Well, it's a pleasure to be here. My computer went to sleep. And it's somewhat of a daunting task because this talk is actually meant to follow another one, which you may not have heard. How many of you have heard me speak on education before? Not many, so okay. The talk that precedes the talk I'm giving today, I'll be giving tomorrow in Rolla. So it's also on YouTube. Just search for Confessions of a Converted Lecturer. Is the PA system a bit loud or not? There might be some feedback at some point, so we may want to get this down a little bit. Converted Lecturer. Just look on YouTube. I gave that talk so many times, I got sick of it. I told the University of Maryland, Baltimore County, it's okay, put it on YouTube. I thought, okay, this way I won't get invited to give that talk anymore. And 1 year it had 35,000 hits, and it's over an hour. And the effect has been the opposite. I've gotten more invitations to give that talk. Anyway, if you'd heard me speak before, you would have seen me use this picture, which is actually me teaching a long time ago. By the way, in Confessions of a Converted Lecturer, what I basically explain is I tell my story, how I converted, in a sense, from being a lecturer, somebody who presents material, to maybe from the sage on the stage, I've become the guide on the side. And instead of being at the center of the learning space, like I'm in this picture here, I coach my students to develop their own understanding. Because the hard work in learning has to be done in the minds of the students, in the learner, not by the person who stands in front of me. I would love to be able to stuff the knowledge into the heads of my students, but I've discovered that in spite of high teaching evaluations, in spite of my students being able to regurgitate material, in spite of my students being able to solve what I thought were pretty complicated problems, they missed the most basic points and therefore did not really accomplish any true learning. So in Confessions of a Converted Lecturer, you hear about that conversion and also about the data that I collected that convinced me that I was not a good teacher, which was an agonizing discovery, right? First, I thought, well, maybe I'm not that good a teacher after all. But that could obviously not be true, right? So I disregarded that very quickly. Then I thought, well, maybe I just have very dumb students. But that's also hard to maintain. And then I started to question the test I'd given to my students, which had not been developed by me. We'll talk about this test in just a second. And in sort of testing the test, I discovered that the real culprit was me. I was focusing actually on, I better plug in my computer, otherwise it's going to go to sleep every few seconds. Or I should use it more often, that's what I should do. That, you know, the process of teaching that is used all around the world and which uses this space that we see here, amphitheater, dating back to the ancient Greek, really focuses completely on the delivery of information. But if you ask yourself, what is education really? Is it just the delivery of information? Think about that for a moment. Is education, what we want to accomplish, is that merely the delivery of information? Who thinks it's the delivery of information? Okay, now I got you in a corner because now you got to tell me what else needs to happen. Since nobody thinks it's the delivery of information, there's something missing. What is it that is missing? What is it that needs to happen?
Discovery.
Discovery. Grasping the information. Engaging the students. Student learning. I mean, I like all those terms, but they're sort of vague, right? I mean, how do you define learning? It's just using one. Education is sort of a word. It's sort of interesting, right? We're all engaged in the process of education. But if we were all to take a little piece of paper out right now and try to write down a definition of education, I think many of us would be struggling. I know I would. How do you actually define what it is, this process of education? kind of weird, right? We're engaged in education, but we have trouble defining what it is. Learning is, I would say, another of these terms, which is rather diffuse. So maybe I'd like to put it this way. What is important is not just the transfer of information, but the assimilation of it. As a learner, you have to take that information and build a mental model so that you can use whatever it is contained in that information and apply it in a new situation. Not just, be as a student, you get the information, right? And then the instructor asks you, what is it that I just said? And you parrot it back. That's not what education is. You have to be able to do something with that information, do something useful, apply it into a new context. Ideally, in a context that nobody has ever seen before, because that's when breakthroughs are going to be made, right? We don't want our students simply to be able to do the same thing, solve the same problems, analyze the same writings as we can do. We'd like our students to stand on our shoulders and make progress beyond what it is that we can do now. Yet I think that a lot of education is not focused on that. It's simply focused on parroting back what we tell them and on solving the same types of problems as we present to them on a little silver plate.
How important it is for you what the students want?
So question is, how important is it for me what the students want? If I pay too much attention to what the students want, I accomplish nothing. They want high grades, and they want to be admitted to Johns Hopkins Medical School. And they don't know yet what is best for them. And that's what a big gripe I have with end of semester evaluations. I have nothing to lose because I get really high student evaluations. But I know that they tell me nothing. Students at the end of the semester, and the problem with many of these end of semester evaluations is they're asked before they've even done the final. Well, I mean, probably you won't know until 5 years after college what it is that is really useful for you. Now, let's think about this for a moment. If you think of education as a two-step process, 1, transfer of information, 2, assimilation of that information, which of those two parts is the hardest? I think everybody will probably agree here. And this is the stuff that has to happen in the mind of the student. Now, isn't it ironic that in the typical approach to teaching, and I'm just as guilty as anybody else, we put all of the emphasis on the easy part, the delivery of information, and leave the hard part to the students? I've often asked myself, where did the assimilation happen for me? Did it happen while I was sitting in the benches listening to my instructors taking notes? No. It happened outside. It happened when I, went over the notes and think, gee, I don't understand this. What was the instructor trying to say here? And while I revisited those notes. Well, shouldn't it be happening for everybody that way? Well, most of my students are not going to become Harvard physics professors or even physics professors. They're going to be doctors. That this may be the last physics course they ever encounter. So I think it's a mistake that we often make. I certainly made it, to project our own experiences onto our students and think that everybody will be like us. Fortunately not, because then the whole world, in my case, will be covered with physicists very, very quickly. So let's do actually a little exercise to get us going, which to basically drive the final nail into the coffin of the lecture. By the way, I have no problems with lectures. In fact, I love lecturing. I miss lecturing because I no longer lecture in the classroom, which is why I'm incredibly happy that Ron invited me to come and lecture to you.
The pride was high enough.
And I think that there is a place for lecturing, right? I'm not trying to teach you here a difficult concept or to develop certain skills. I am just trying to convince you of a couple of messages, one of which is that the lecture is an ineffective approach, although if you want to hear more about that, you'll have to look at that lecture or hear my lecture tomorrow in Rolla. Another message I'll give in a second. But let's do a little exercise. Take a little piece of paper and a pen, right? Or anything you can write on, smartphone, whatever, laptop. Something you can jot down something. And what you're going to write down is going to be totally private, okay? You're not going to have to reveal it to anyone. So you can write down whatever you want. I want you to commit to paper and then hide it, okay? Something that you know you are really, really, really good at. Something ideally that has helped you advance your career, right? So it could be solving partial differential equations. It could be, you know, communication skills. It could be interpersonal skills. It could be playing tennis, whatever. It doesn't matter. But write down something you're proud of. And if it's connected to your career, even better. It's likely to be connected to your career because we tend to choose careers in areas that we're good at. Right? Why other choose that career? I see some blank stares. Now, you've all been very successful, so it shouldn't be too hard to come up with something you're proud of, some skill, some ability, some knowledge. Maybe you know a lot about American history or American literature. Okay. Does everybody have something committed to paper? Okay. And again, fold it up because, you know, it's private information. You don't need to reveal it to anybody. But what I would like you to do next is this. I would like you to think about the circumstances that led you to become good at whatever it is that you wrote on your piece of paper. How did you learn it? How did you become good at whatever it is you wrote down? I still see some people scribbling, so I'll give you another few seconds. Don't worry, it won't be on the final exam. Okay, so everybody ready? Go to see a show of hands. How many of you wrote down lecture? Don't be afraid. If you wrote it down, raise your hand, please. Nobody wrote down lecture. Nobody. I've done this many times, you know, and we've all become successful, and we all have skills that have helped us become successful. But what people write down is, you know, apprenticeship, trial and error, you know, by studying myself, by making mistakes. It's very, very rare. I've tried this exercise with many audiences that people actually write down something related to a formal educational setting. That tells you something, doesn't it? And yet, for some reason, we stick to this antiquated method here. Anyway, so that's really a message that I bring much more forcefully and motivate a little bit better in my other lecture. I will assume that we all agree, and we seem to be agreeing, at least in principle, on that issue. What I would like to do today is to touch on something else, and that's the following. Namely, that a lot of discussion about education, especially in my environment in the sciences, is, you know, sort of using anecdotes and gut feelings, and people do not have the same scholarly approach to studying how people learn as they do in their own disciplines. Especially if you take my own physics department, for example. When I joined in the early 80s as a professor, there were 6 Nobel laureates out of 27 professors. But whenever the discussion would turn to teaching, the most distinguished scientists would completely abandon any scholarly approach or any scientific method. My students learn better when I do a lot of demonstrations. Well, how do you know they learn better? Or my students like it when I do this or that. what does it matter whether they like it or not? Do they learn better? How does it help us accomplish our goals? So I think that something that is really important is that we apply the same rigor, the same scholarship to our teaching as we do in our own disciplines. Lee Schulman, former president of the Carnegie Foundation, has an absolutely marvelous quote, which I love to use whenever a colleague of mine comes with anecdotal evidence about teaching rather than real evidence. And the quote is as follows. It's very short. The plural of anecdote is not data. You don't validate an argument just by giving a lot of anecdotes. So I would like to show you how I, in my own teaching, use the classroom, in a sense, as a laboratory for collecting educational data. And by collecting data, I can show whether or not something I do in the class has an effect, a desired effect. If it does, so much the better, then I keep it. If it doesn't, then I change it. And I've learned a lot. And in this talk, what I would like to do is basically give you a broad overview of a few of the things that we've been able to learn by collecting data from the classroom. It's just a very broad overview. Two are published, the first two. One deals with gender issues. The other deals with lecture demonstration. And one is still ongoing and not yet published, deals with the subject of confusion. So I'll spend maybe about 10, 15 minutes on each of them, and then I hope we can have a discussion. So let's start with gender issues. What got me to change my approach to teaching from the passive lecturer to somebody who facilitates discussion among the students, and I'll tell you a little bit more about what I'm doing in just a second, was a conceptual survey of the concept of force that was developed by a professor at Arizona State University by the name of David Hestenes. This test is called the Force Concept Inventory. Basically, let me tell you, since you're not probably all physicists here, I'm sure you're not, let me tell you a little bit, and I should also add a caveat here. I will talk a little bit about physics here, but the idea is really independent of the discipline. So if you're a chemist, substitute chemistry whenever it's physics. If you're in the English department, you can do the same thing. The examples will be different, but I think that some of the basic principles still apply. Now, in the physics curriculum, in week 1, you start by describing motion, velocity, acceleration, and so on. Then you build on top of that by adding the concept of force, connection between, if you want, mechanics and motion. And the force, the concept of force, is basically embodied by Newton's 3 laws. All the force concept inventory really does is test students' mental model of force. In weeks 3, 4, 5, you build on top of this concept of force, and basically everything hinges on a solid understanding of the concept of force. If you do not understand the concept of force, the rest of physics is really wasted on you, because it's very hard to make any real sense of it. The best you can do is parrot back information or try to memorize things and write down the right things, but it will not make any real sense. And unfortunately, I'm afraid I have to admit that it happens for a relatively large proportion of the students that that's the only thing they accomplish. Anyway, the FCI, you can give it as a pre-test and a post-test. It asks questions as follows. A heavy truck and a light car collide head-on. Is the force of the heavy truck on the light car larger than that of the light car on the heavy truck, equal to, smaller than? And what you find is that in spite of the fact that students can recite Newton's 3rd law, which says the force of A on B is equal in magnitude to the force of B on A, when A and B are replaced by truck and small car, they forget all about Newton's 3rd law, and they're convinced the heavy truck exerts a larger force on the small car than the other way around. Now, because this question is phrased in everyday language, force is a physics concept, yes, but it's also a word in daily life. You don't need to be a physicist to have a mental model of what is meant by the word force. You can ask this question at the beginning of the term as a pretest, and then repeat it at the end of the term as a post-test to see how much instruction is done to change the mental models. And Hestenes showed, for example, that regardless of the quality of the teaching, the evaluation of the teacher, I should say, students learned very little in their introductory physics courses. They clung to their beliefs that they had at the beginning of the term. I thought, no way. And that's when I discovered that it was not much better at Harvard, and that made me change my approach. But another thing that we noticed over the years, and we also got similar data from another institution, the University of Minnesota, showed us that if you take the post-test scores, so post means at the end of the semester, and you separate them according to gender, you find that there is a gap in performance between the men and the women. These are data actually from the University of Minnesota. I want to start there to show that it's not different from my own institution. So if we look at this gap and we plot it, it's about 12% at the University of Minnesota. If you look at 2 of the Harvard courses I have taught, different levels. One is they're both non-major course. One is for pre-medical students. The other is for engineering students. Not much difference. And Worcester Polytechnic Institute, also a similar gap. So 3 very different type of institutions, different level students, a gap between the men and the women. So what causes this gap? And these are data that I have not yet published because I need much more data to make them more significant. But I have the benefit of getting to spend some sabbaticals every couple of years. And usually when I'm in a foreign country, I try to convince my hosts to administer the FCI at their institution. So here's sort of the average US gender gap on the FCI, now comprising quite a few institutions, and the bar is actually quite small. I spent my first sabbatical after becoming aware of the FCI in Belgium at one of their leading engineering universities. And I managed to convince them to administer the FCI. We translated it from English into Dutch, Flemish, but it's the same thing written. And since I grew up in Holland, and it's one of my mother tongues, I was able to check the accuracy of the translation. And after giving the FCI, I was called in by the dean, and I had to promise that I would never reveal the identity of this school. And the results were fairly abysmal. You know, it's strange because I had given the FCI in the US, but I was educated, as you heard, in Europe. So I thought, you know, in Europe we get a really solid education, and I'm sure that people do a lot better on the FCI in Europe. It's funny how you tend to see everything through, you know, your own eyes and your own experience. You experience something a certain way, you think everybody else experiences it the same way. Wrong. They did really, really poorly. What's more, the gender gap was even larger than in the US. And the difference is statistically significant. Next sabbatical, I was in Taipei, at Taida, which is National Taiwan University, the flagship university in Taiwan. My first 4 graduate students in the mid-80s were all Taiwanese, and they all went back to faculty positions at Taida. So when I got my first sabbatical, they said, oh, come and spend it with us. And I ended up spending a sabbatical there. And I thought, great, we're going to try the FCI at Taida. They were still pretty junior faculty at Taida there. So they had to ask their more senior faculty colleagues whether it was OK to give the FCI. Senior colleagues look at the FCI, and they said, you're totally crazy. This is high school stuff. We can't give it here. I mean, I lost all respect there right away because saying that even at Harvard we had students do poorly on them did not impress them at all. On the contrary, that I could see them thinking, we're not going to send any graduate students to Harvard anymore. So I was unfortunately unable to collect data at Taida. Although I must tell you, last year they invited me specifically for a conference on education at Taida, and they became very interested, and I think there's a good chance that we'll finally have some data from the flagship University of Taiwan. And I can already tell you there won't be that much difference because I've given this now in so many different environments that I know that in any environment where people have just, you know, the approach of we teach and people learn from listening to us, the gains are very small. But what did happen was that there was another college nearby called Taiwan National Normal University, a teacher training university, which was very interested in testing their students. So took the FCI, translated into Chinese. My people at the National Taiwan Normal University translated into Chinese. I had my graduate students translated back from Chinese into English because I wanted to make sure that none of the nuances were lost. And we gave it. And two surprising things. One is, even though this was not the flagship university, it was a teacher training university, the average level was comparable to that of Harvard students. So really, really high compared to what you would find across the US. But secondly, there was no statistically significant gender gap. There is a little there, but it's not statistically significant. So the noise is larger than that bar there. Any differences between these three universities? Well, there I have to unfortunately rely a little bit on anecdotal data, or maybe not anecdotal data, but data that are not solid because the numbers are small. Belgium, not a single female faculty member, completely male-dominated department. Taiwan, at this National Normal University, about half the faculty were female. So it was definitely a very different environment, and from the perspective of a student, probably a very different feeling to see so many more role models who were female. In the US, in physics, in my department right now, we have about 1/5 to 1/4 women, but it's certainly not a gender balance. So, but what does this tell us? This tells us that that gap is not something inherent or anything. It's something that is actually different culture by culture and that can be influenced by the environment, as one would expect. So what about the effect of pre-college education? Some of the students that I get at Harvard, we're back to Harvard here, have had no high school physics whatsoever. Others have had a high school physics, and others have had an AP physics course where they usually score 5. There's a slight correlation between the scores on the FCI and their pre-college education, but not very much, as you see. If you get a 5 on the AP, you would expect students to score 100%, because don't forget, this is what you get sort of in the second week, and everything else builds on it. It's actually shocking to see students come out of an AP with a score of 5 and only score 70%, telling that they're still partially Aristotelian thinkers rather than Newtonian thinkers. What about the men? Well, the men score higher across the board. And you see that both the women and the men seem to benefit from more pre-college education, but the gap persists. What is more, women are underrepresented among the higher level. For example, whereas there are roughly equal numbers of students who have had high school physics, there are far fewer women than men who have done AP physics. So that makes, I think, the picture a little bit less rosy, even less rosy. So what can we do? Is there something we can do at the college level to address this gap, right? Given that culture can have an influence, maybe there's something we can do. And there's been quite a bit of research in gender differences, and a number of researchers have claimed that if you make the environment more collaborative and less competitive, more verbal and less quantitative, you can actually help females do better. Now, the type of approach of teaching that I've developed, which I won't have much time to speak about, but I'll just give you the upshot, is this. Rather than lecturing, I have the students either view a video of a lecture before coming to class or read the textbook before class. So the information transfer is out of the classroom. And in the classroom, we focus on the assimilation of the information. And we do that by me asking them questions. So I'll ask them a question. They think about it. Then they use a clicker that started about 19 years ago in my classroom. We had wired calculators first, and then later an alum of the School of Engineering made these infrared clickers, and now it's a whole industry. I wish, I was so focused on the pedagogy that I didn't think of the hardware as being something interesting. I wish I had jumped on the bandwagon. But anyway, so they click in an answer, and then I tell them, now find a neighbor around you who has a different answer and try to convince that neighbor of your answer. total chaos in the classroom. They forget about me in front of the classroom completely because they're so thinking about, oh, the water level goes up. No, 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 it goes down. And they start to think about the reasoning rather than just the answer. And then I have them vote again. So I thought that, you know, maybe that this approach to teaching, which increases interactivity and collaboration, will actually benefit the female students disproportionately more than male students. It benefits everybody, but female students more than male students, so that we close this gap. So I decided over a period of years, I think close to 10 years, I'll have the reference of the publication soon at the bottom of the screen if you're interested in more. Namely, I compared traditional lectures, all taught by me, okay, to interactive lectures, as I just described, to Interactive Plus, where not only the lectures were interactive, but all other activities were interactive too. So homework was done in groups. Discussion sections were not done in an environment like this, but round tables with students sitting around the round tables helping one another, and the staff going from one table to the other. So always student-focused rather than instructor-focused. So let's compare the effect of these three different pedagogies on the learning in the classroom. So we start by looking at the pretest. So this is at the beginning of the semester, over a large number of years, this is about 10 years, between traditional, interactive, and interactive engagement plus. And as you see, there's not much difference, but there shouldn't be any difference because they haven't been taught yet, right? And I'll use this little triangle here in this, at the side to show what the average pretest level is, because we're going to look at the post-test. That's what we're interested in, right? But just to jog your memory, that little triangle there on the left shows the pretest. What about the man? Well, there's a little bit of variation. Turns out that when we use this technique, they scored a little bit lower, but that doesn't matter really. It only makes the picture better than it is. So this is the average post-test. So I'm only going to maintain those two little triangles. What about the, did I say post-test? I meant pre-test. Okay. What about the post-test score? Well, here are the scores by the female students. And as you can see, they gain more and more as the interactivity goes up. The man too. But notice that the gap disappears. In fact, at the top there, the gap is no longer statistically significant. So the more the interactivity, the better the performance of the female students relative to the men, which is great because that means we can, even if there is a gap, we can address it at the college level. And if you also look at the distribution of genders across low and high performance, you see the same positive picture emerge. This is a data point for a single student. This student started out with a pretest of 70 and then ended with 90 because he or she, this was a she, blue, gained 20%. So if we plot on this graph the gain versus the pretest score for all of the female students, we get this distribution. And for all of the male students, we get that. This is in a traditional class. And if you look at the distribution around the mean, you see that there are disproportionately more women below the mean than there are men. If you do that same plot for an interactive class, you see all the data points move closer to the diagonal because you've lifted the performance of everybody. And now there are not more female students and lower performing. There's much more gender balance there. So what does that mean? It means two things, I think, we can conclude from these data. That any gender gap comes from whatever culture and background there is, and is something that we can address. I think that's the big, you know, bright light of hope that we have there, and that interactivity is one way that we can actually address this gap. Feel free to interrupt me at any time, okay? Yes?
I think the other thing that just resonates so much with me is when I work in the Center for Student Success.
Can everybody hear? Can you stand up, perhaps?
I work in the Center for Student Success, and I work with students who sometimes have academic difficulty, and one of the challenges that some of them have is when they work in work groups, some of them are not always fond of that. And I like this approach because it encourages students to practice those teamwork skills, which some of them could develop more strongly than others, which I think really is mirrored in the real world. You know, when they leave college, they're going to be doing that. And so I think I find it frustrating when we, and sometimes necessary, encourage them to work on their own, do it on your own, do it on your own, when really, in the world, you know, if they're going to be physicians, we want them to be consulting with their colleagues. And this is exactly what they do, you know?
Absolutely.
I want to go see a physician and have me consult with someone else.
Absolutely, absolutely. The same is true for the assessment. I mean, I had a very interesting discussion with a couple of chairs before this talk, and one of the things I said, and I think I'll repeat it here, is that when we assess our students, when we give examinations, we often put them in an environment that is so unlike any of the environments we normally have, right? You're sitting at a table, isolated from everybody else, cut off from all information. No book, no notes, nothing, no computer, right? You gotta, and then you have to work in that bubble, that isolation bubble, and do well on the exam. You know.
Don't get anxious.
But don't get nervous. Exactly. I was just you anticipated what I was going to say. I now tell my students that they can bring whatever they want to the exam. Books, notes, computers, cell phones, smartphones, whatever they want, everything. Because when I do my work, if I write a paper, I can look up whatever I want. Okay, true. 20 years ago, if I didn't know what Planck's constant was, I was in trouble because you can't afford to run up to the library each time you need Planck's constant, right? But now I can pull out, oh, I took my phone off. But I can pull out my phone, press the Google button and say Planck's constant. And a second later, Planck's constant shows up to many more digits than I could possibly remember. And you know, and when I write a paper in Phys Rev Letters or Science or Nature or whatever, there's nobody standing next to me saying, oh, you're not allowed to look up the paper from this colleague of yours. You should have known it. I can look up whatever information I want. It's not about memorizing the information. It's about knowing how to use it. And I think that sends two very strong messages to the students. Well, no, two very strong messages. One to the students, one to the assessor. To the students, it says, well, you know, memorizing is not going to help you because you're going to have access to the information. The memorization should come from using the information over and over, the same way we learn a language or any other skill, right? When we learned our language, we weren't drilled on, you know, this is how the grammar is, and you know, we tried. And probably along the ways that you wrote down on the pieces of paper that you learned the important skills in your own discipline. But the much more important message was sent to me. Because all of a sudden I discovered that most of the questions I used to assess my students were meaningless. Because students could just look them up in the book. Now I have to think, how am I going to actually assess that they can use the information that they have in a creative manner? So I urge you to consider that. I went in several steps, you know, especially the laptop thing. I was really worried about that. And it's only this year that I've started to allow laptop. I said, what if they use instant messaging? You know, and what if this or that or the other? There's no time to use instant messaging. And they could check the answers, but it's not about the answers, it's about the reasoning, and there's no way they can communicate all of that to each other. So right now, I just let them use whatever they want. And I make sure that my question tests the type of learning goals that I want to accomplish. Anyway, I'm on a sidetrack here, and I should get going if we want to get through this talk before dinner. Yes?
So do you still see a typical bell-shaped curve for all of your exams that you administer, regardless of your approach to conveying the information?
Well, it's been skewed a little bit towards higher grades, also because I push the students in class, and because I have decided that I don't want to put too much weight on just exams. I want to find other ways of assessing their knowledge. So I give quite a bit of weight to preparation before class, to participation in class, and to problem sets where I push them a lot harder on homework now than I used to do. Right? I try to have them, my homework sets are really, really hard. They work very, very hard on it. But they have as much time as they want, and they're pushed to collaborate on those aspects of the course. So that has pushed the course grades up a little bit more, and it's relieved them from this anxiety that you have when you're put in a standard exam situation. But if you look at how well they do at the end of the term, as assessed by a number of metrics, one, performance on standardized instruments like the FCI, but two, their ability to solve problems they've not encountered before, right? I tell my students, look, you're always going to be assessed on problems you have not seen before. Right? Because I used to always have students who would come to me after the exam and said, Professor Mazur, we've never done such a problem. Well, if you've done it before, it's no longer a problem, right?
Do you think there's an effect in that they have to prepare more diligently when they have to confront their fellow students the next day also?
Yes, we'll get to that in just a second. Yeah. Let's first talk about demonstrations. Have some fun. I'm an experimentalist. To me, there is no better way of learning than seeing, right? In other words, if you want to learn how the universe works, observe how the universe works, and if the universe tells you it works in a certain way, then, you know, that's it. Well, that was a pretty naive belief, I found out. I visit very often the University of Washington in Seattle, where there's a well-known physics education research group by Lillian McDermott. And I was speaking a number of years ago to one of her graduate students who had interviewed students at the end of the term, and one of the things she had interviewed them about was their memory of observations that had been done in the classroom. One very famous demonstration in physics is shoot the monkey. You have a monkey suspended by an electromagnet, and you aim a gun at it, and you fire the rifle. It's not a gun with powder. It's a spring-propelled gun, right? And the moment that the projectile emerges from the barrel, it trips a wire, and the monkey starts falling. So you aim exactly at this monkey, and then just as the projectile leaves the barrel, the monkey starts falling. But then the projectile goes and still hits the monkey. Why? Because both are subject to gravity and both fall at exactly the same rate. So no matter whether you fire fast or you fire very slowly, the bullet always hits it. Well, she found that some students remembered that the monkey was hit by the projectile, but they were convinced, even though the whole point of demonstration was to show that that was not the case, to use a laser to show that the barrel is aimed exactly at the thing. She was convinced that you had to aim a little bit below the monkey in order to hit it. Well, the whole purpose of the demonstration was to show that you should not. Right. Anyway, so I thought, wow, that's amazing. And we decided to actually carry out, this was a 2-year study, a number of demonstrations, actually more than 7, but I'm going to report only on the first batch of 7, in 4 different modes. We took a class of about 200 students and separated them into 4 groups. The separation into 4 groups happened when we had the discussion sections. There were actually 8 groups, but 2 groups were in each of one mode. One mode was no demo at all. So those sections did not get to see the demo at all. In the second 2 groups, we had the demo in observe mode. We told the instructor to do the best possible job explaining the demo in a standard presentation fashion. In the third category, we had the demo set up, but then we projected on the screen a drawing that showed the demo schematically and asked the students to predict the outcome. And then we had a clicker question where they had to vote, you know, this is going to happen, or that's going to happen, or that's going to happen. So they had to think about the demonstration before seeing it and committing themselves to a prediction of an outcome. Then we did the demonstration. And then we had a 4th category called discuss, where the demo was set up, and the students got a worksheet, which at the top had a schematic representation of the demo, and the students were, in free response style, asked to write down what they would predict, what they predicted would happen. Then we did the demo, and they had to write down what they had observed. And after writing down what they had observed, they had to check a box. My prediction does or does not correspond to my observation. And then we gave them 2 or 3 minutes to talk to their neighbors to resolve any inconsistencies between prediction and observation. And then we rotated the students among the modes. So for example, you know, this group may be no demo in week 1, but the next week this group is no demo. And so that, you know, we didn't have any bias by the selection of the students. Okay. So obviously, there's more time investment. This takes no time at all. This takes whatever time the demo takes. Here, you add another 2 minutes for the students to think about it and commit themselves to a prediction. And here, it takes another 8 minutes because they have to fill out the thing. So there's considerably more investment in time in this last category. Let me give you an example. Oh, before I do that, what did we do then? Then at the end of the semester, we had a free response online test, which tested their memory of what they had seen. And then it also checked whether or not they could take whatever they had seen and extrapolate it to a new situation. And then we had an exam. No group admin, I'm not there. And they had an exam question that took whatever the demo was, put it in a completely different context, and then saw if they could apply whatever they'd learned in the demo in that totally new context. So here's one demo. You have 2 scales, and you have a plank on top of the 2 scales, and an object in the middle, and each scale indicates half the weight of this object. Okay? Then the object is moved to the side, and a very common misconception, even among Harvard students, is it doesn't make any sense where you put the thing because the plank evens out the load. Well, it doesn't. Anybody who has lifted up something that's much heavier on one side or the other knows that, you know, it's better to lift it up on some side than on another. But you have to balance not only forces, you also have to balance what are called torques. And those this demo is typically done in the context of discussing torques. So that was the demo. And then the online test question at the end of the semester was quantitative. We gave this drawing, 10 and 10, and they had to fill in the blanks. So this was the memory of the demonstration, and this was extrapolating it, right? It's a quarter of the way rather than half the way. So let's look at some of the responses. 24% of the students at the end of the semester gave the correct answers, 20 and 0, 15 and 5, and correctly mentioned torques in their explanation of why they had given those numbers. Another 38% of the students gave the same correct answers, but did not really mention torques. They had some proportional reasoning to go. Depending on your point of view, you may say either 24% is correct or 24 plus 38. 20% of the students, 20% of the students said it doesn't make any difference. In fact, I had one student, you know, I thought, okay, that's going to be the 20% who didn't see the demo. False. I had several students write down, as shown in class, it doesn't make any difference. I got so excited when I saw that. I thought, you know, I've discovered a new psychological phenomenon. I went to Pat Cavanaugh, a friend of mine in the psychology department, and I said, look, you know, I have something so exciting to tell you. I did this demo, and then I asked students later, and they wrote that they had seen exactly the opposite of what I tried to show. And he said, of course. And I said, what do you mean, of course? Well, I mean, imagine you're a student, and you have this wrong mental model. The mental model you have is, it doesn't make any difference where it is on the plank, because the plank evens out the load. Now you're in class, and the professor, the instructor, does this demo, and the scales, instead of staying put, go like this. You have what Piaget calls a cognitive dissonance. You go, whoa, wait a minute. Maybe you quickly scribble down a note. You know, it's not a... But before, this is the key point, before you have time to think about it, the instructor goes on to talk about other things. The note remains in your notebook. The cognitive dissonance slowly fades away. And rather than adjusting your mental model to the observation, you adjust your memory to your wrong mental model. Something psychologists have known a long time, because the way the brain works is not by storing facts. The brain works by storing mental models. So if you have the incorrect mental model and you don't have an opportunity to revise that model, you're going to adjust your memory to the wrong mental model. 10% of students had only a qualitative reasoning, so they didn't give numbers. 6% of students, the forces were not balanced, so if you added the two numbers, they didn't add to 20. All of a sudden, the whole thing got a lot heavier or lighter. I don't know how. And 2% made other incorrect mistakes. Now, if you plot the number of students who get it correct in the 4 categories for this particular demonstration, that's what you see. Now, look at that. 18% correct in the observed category, less than in any other. Is just presenting harmful? Well, take that one student who said, as shown in classes, it doesn't make any difference, right? The student had adjusted his or her memory to the wrong mental model and now used this incorrect memory as evidence that that reasoning was correct, right? You actually rub in the wrong mental model even more. Well, that's only one demo. Let's actually look at the follow-up question too, so you get an idea for the method of testing. So here's the same question, but a very different context. Now we have a plank suspended by 2 ropes, and we give them the tension in one of the 2 ropes, 150. Well, it's symmetric. That means the other one also has to be 150 Newton, which means the plank weighs 300 Newtons. And the question is, if we move that one rope at Q over 1/4 of the way to point R, what are the tensions in the rope? Looks very different, but it's exactly the same concepts. You have to balance forces and torques. How did the students do? Well, 36% of the students, 30% with correct reasoning, gave the right answers. 100 Newton and 200 Newton, adding up to 300 Newton. Here are some incorrect answers. 13% of the students said 150 and 300, so all of a sudden it doesn't add to 300 anymore. Others gave 75 and 225. Both of these were due to incorrect determination of the lever arm. And then there was something really strange. I scratched my head a long time over that. 8% of the students gave these weird answers. 112.5, this is 16 students, okay, so it's not negligible. 112.5 and 187.5. And some had 112.5 and 112.5. The only thing I could figure out was that 112.5 was 3/8 of 300, and that was 5/8 of 300. This is just to amuse the physicists and engineers in the audience. Do we have physicists and engineers? Okay, some. Any idea where those numbers come from? As always, with misconceptions, it's just a very simple idea, but you know, once you know the right answer, it's very hard to forget a simplistic view of looking at it.
It's like the ratio of the distances, but there's got to be something else.
Wow. I finally figured it out because one student actually wrote it out. Here. It's very simple. Take this plank between the 2 ropes. 1/2 is going to be supported by this. So that's 1/2 of 3/4. That's 3/8. This half goes with that rope plus that. That's 5/8. And these 2 students here said, well, no, this part of the plank no longer needs to be supported because it's outside. Who would have thought, right? It shows how much you can learn from analyzing mistakes. I used to focus on the correct solutions and never really think hard about mistakes that my students make. Now, whenever I correct anything, I have a piece of paper and I write down the mistakes they make because it's so illuminating. It's like having a window into the brains of your students. Okay, so what about here? Well, you see some correlation with the amount of time invested from 31 to 46, but not that much. But if you look at the reasoning, you see that those who have actually talked about the demo do significantly better than the other. So that was just for one. What about all 7 demonstrations? If you look at the aggregate, and then we have many more data points, so it's much more statistically significant, you see that the ability to predict the outcome correctly, or remember the outcome correctly, goes up consistently with the level of engagement, and to the ability to provide a completely accurate and correct explanation also increases much more dramatically by 50%. So that's the article in which we published that. And this shows the same thing graphically. You can see, using the no demo group as a control, you can see how much the gain is from just observing, just predicting, and then discussion. This is just the ability to correctly give the outcome. But the explanation, there's much more significant gains. So what does this tell us? One is that just doing a demonstration is not very helpful. It can even be counterproductive. But, and I think this is the bright light again, is that you can increase the results, you can improve the results significantly just by having the students predict the outcome. That's a minimum effort, right? Because it just takes a few minutes. The discussion is a lot more work. And if we go back to this graph here, this improvement is not as significant as this improvement or that improvement, right? But this is a significant larger investment in time. So just giving your students the opportunity to think about it before they see it is a significant help. Okay, I promise I'll finish in not too long, but I want to talk briefly about this confusion because this is something that I'm really, really excited about. As an instructor, you're usually praised for giving clear lectures. In fact, I would not be surprised if in your end of semester evaluation, one of the questions asked to the students is, Professor, gave clear lectures, if that's an actual evaluation criterion that your students are evaluating you on. And you know, in general, confusion is seen as something that's discouraging and is to be avoided. Right? Confusion is bad. However, we all know that to wonder is to begin to understand. You don't learn by just, saying, boom, stuffed in my head. No, you go, wait a minute. Why is it like this? And then thinking about it, being compelled to think about it because you are, somewhat confused. And then thinking, I got it. Resolving that confusion and going, you have to go through that cycle in order to really internalize information. And I had used a system in my class to prepare my students where basically before they come to class, they have to do some reading and they have to tell me what they found difficult or confusing in the reading. And I have a system where which actually shows a picture of the students, the name of the students, and what they found difficult or confusing in the reading. And the first year that I saw that, I had many students who would say nothing was difficult or confusing. And look at the picture and I think, this is not one of the better students in the class. Click on the picture, and low midterm score, low problem set score. So how can that student not find anything confusing? And then another student said, I didn't understand this, I'm confused about that, what about this one? A whole laundry list. This is one of the better students in the class. So I had this anecdotal feeling that there was an anti-correlation between the performance of the students in the class and the expressed level of confusion. So I thought, does confusion actually indicate a lack of understanding? Or maybe the inverse of this statement, does lack of confusion indicate understanding? So I decided I was going to actually use this method, this just-in-time teaching, which was developed by a number of people in Indiana, and this is the book that describes it, to test this. You give students something to read, and then you pose 3 questions. 2 questions are on the content, and they're very difficult. They're not just look it up in the book. They're no, read the book, think about it, and then answer the question. But the students are told that it doesn't matter whether they get it right or wrong. Well, ideally they get it right, but what matters is that they convince through the answer that they write down that they've done the reading. So they basically have to show familiarity with the subject, which is much easier to evaluate too. And then the last question is feedback question, which basically is always the same, and which elicits their confusion. And then I decided to analyze the understanding on certain concepts and correlate it with the confusion. Let me give you an example. And again, it's physics, but it's irrelevant. You could substitute anything else. This was on the subject of fluids and capillarity and Laplace's. Here's one. There's the drawing. Consider the capillary rise of a liquid in a glass tube. How does the pressure at point P at the surface of the liquid compare to the pressure at point Q at equal height? Well, if there were a pressure difference, then the fluid would flow horizontally or vertically. So they have to be equal at the same height. That's determined by gravity. Second question, two identical balloons are connected to a tube as shown below with a little valve in between. Balloon B is inflated more, meaning it contains more air, than balloon A. Which way does the air flow when valve P is opened? Now, that's a very curious and counterintuitive thing. The little balloon empties out in the big one. If you've ever blown up a balloon, you know that in the beginning, it's really hard to get the air in, but once there's air in, it's much easier to blow it up. The reason is that as it's small, the rubber is very curved. As it's very curved, the rubber can pull in more and create more pressure inside the balloon. So once it's more blown up, the rubber does much less to press the air in. It's a very important phenomenon for pre-medical students. Prematurely born babies before 22 weeks die because what happens is exactly what happens when you open this little valve. Little balloons, in their case, little alveoli in the lungs, collapse into bigger ones, and the bigger ones burst because they don't have a liquid, a surfactant, that coats the inside of the alveoli that equalizes that surface tension that is responsible for this pressure. I was using a book that actually pointed it out. I had selected a book that year that gave a lot of examples in a medical world because it was a pre-medical course. I thought, by connecting the physics to phenomena that appeal to these types of students, I'll have more meaning to them. And the third question, please tell us briefly what points of the reading you found most difficult or confusing. If you did not find any part of it difficult or confusing, please tell us what parts you found most interesting. So by just saying nothing was confusing, they don't get credit. They can say nothing was confusing, but then they have to say what is interesting. Okay, so let's look at two student answers here before I give you the analysis. Capillary action is due to the cohesion between water molecules and the adhesion of water to the surface of the glass tube. A sentence more or less literally copied out of the textbook. True, it was in the textbook, and therefore a correct sentence, but I don't know what to do with that information. Negative pressures can result from the cohesive forces of water. Another sentence plucked from somewhere else in the book. At the same height, the pressure inside the tube is much less due to negative pressures. I can't follow the logic. I'm not sure what it means, but in any case, it's wrong. The air flows from high pressure to low pressure. Very good. The fully blown up balloon has higher pressure than the half blown up balloon. I'm sorry, that's wrong. So the air flows from the fully blown balloon to the half filled balloon. Now look at the answer to the last question. Nothing was difficult or confusing. The sections on the surfactant in the lungs and the heart as a pump were interesting because they relate physics to biology. Okay, that's one student. Let's go to the other extreme. The water rises because of an interaction between the water and the walls of the tube. The meaning of that sentence is actually the same as that first sentence from the other one, but the student has taken that information and put it in his or her own words. This interaction creates an upward force which causes the water to rise. This force is due to surface tension between the water and the walls of the tube. The pressure at the point inside the tube must be the same as the pressure at the point of equal height outside the tube, because if there was a pressure difference, there would be a net flow of water into or out of the tube until the pressure difference was equalized. Fantastic, the correct articulation of the ideas. I mean, it's just fantastic. Question number 2. Laplace's law tells us that it requires a greater pressure difference to maintain a small sphere than a large one. So the pressure in the small balloon must be greater, and the air will flow from the small balloon into the larger one. Brilliant. Now look at the last question, answer to the last question. I found the explanation of Laplace's law to be inadequate. And while I can understand the conclusion drawn, I don't understand the reasoning which led to the conclusion. Okay, so I decided to take all of the 200 responses and code them. First of all, see if the capillarity question 1 was correct or incorrect, and question 2 correct or incorrect, and then see in question 3 whether they mentioned any confusion on either capillarity or Laplace's law. So this student would be ranked correct, correct, confusion on Laplace, the second one, but no confusion on capillarity because he or she doesn't say anything. This student, on the other hand, would be wrong, wrong, no confusion, no confusion. Okay? And then I decided to do it for all of the 200 students, and I'm going to show you the averages, and it's very illuminating. Of the students who said they were confused by capillarity, who explicitly mentioned being confused by capillarity, 44% got the question on capillarity correct. Of the students who did not mention confusion on capillarity, only 25% got it correct. And on the Laplace's equation, Laplace was almost the same, 49%, 21%. So students who are confused are twice as likely correct. Now, in hindsight, it makes a lot of sense, right? The students who were not confused were not confused because they understood everything. They were not confused because they hadn't even begun to understand. They just read over it without any struggle, without any questions, without any questioning what it was there, maybe make a few notes, but no attempt even to internalize the information. I repeated the study years later using a research-based text which compels the students to think while they're reading. In other words, you can't read through the text every little bit. There's a question that forces you to think about what you've just read. And there was not a very significant difference between the two because they had already begun to think about it. So what does this mean? And I'll stop here, is that there is more confusion among students who understand, especially when they're not pushed to think. As I said, that's not that surprising. However, and I think this is important, is that it is potentially a huge barrier to improving instruction, right? Because as you're trying to push your students to understand the material better, you get not fewer confused students, but more. When I gave my brilliant, clear lectures that got me the high student evaluations, but very poor performance on the FCI, students walked out of the classroom thinking they'd heard the most clear lecture ever, but they didn't learn anything. Now, when I use peer instruction, and the students talk to their neighbors and think and so on, and they tell me what they're confused about in the reading, they walk out of the classroom with millions of questions. Now, from a student point of view, that's an uncomfortable feeling, right? You much rather walk out of the classroom saying, I nailed it, right? I can do this. And for an instructor, it's also intimidating. You know, I would give a lecture and I would say, does anybody have a question? No questions, you know, it's been so clear, there's no questions. Now, with peer instruction, Professor Mazur, what about this? And if the water goes up there, you know, there's just one question after another. There's no time to answer all the questions. So it would be very easy to be misled to thinking that we've gone in the wrong direction rather than the right direction, which is why I think it's so important to get this message out. So, confusion does not correlate with understanding. It's not necessarily the result of poor teaching. I'm not trying to say that poor teaching would not result in confusion. So good teaching could also confuse. And I think it's an integral part of the learning process. You have to go through this step of confusion. Of course, you've got to go beyond it too, but you cannot avoid it. So the main point, I hope to have convinced you that gathering classroom data is absolutely instrumental to improving instruction. I'd like to acknowledge several of my graduate students and staff who have helped with this research. And if you're interested in a copy of this talk, you can go to that URL there. You don't need to remember it. Just go to Google and then enter my last name and hit this I'm feeling lucky button. And click after that, you'll have a copy of these slides. Thank you very much.